last lecture, we have briefly talked about the theory of multidimensional unconstrained optimization, and we have seen a couple of examples on that. Now in subsequent lectures, when we will try to solve such problem numerically, we'll see that gradient will play a big role in such optimization. Therefore, in this lecture, we'll stop a bit and we'll take a look at what gradient does in case of multidimensional problems. Let us start with a simple elliptic curve x square plus 2y square minus 2xy minus twice x. In last lecture, we have minimized this function f, but here we are taking a particular value 7, and for that the plot will look something like this red curve. Now, if we differentiate this f of xy, then what I'll get is differentiating everything with respect to x. I'll get here 2x, here 4y dy dx, here 2x dy dx and 2y, and here 2x will come as 2, 7 will come as 0. From this expression, I can find out the expression of dy dx, which will give me 2y minus twice x plus 2 divided by 4y minus twice x. If you remember the gradient of this function, you will recall there is a relation between this dy dx and that gradient. My suggestion to you is to go back in previous lecture and explore the relation. But now let us take a point on the curve -1, 1, and the value of dy dx at that particular point is 1, which means that if I draw a tangent over this curve at this particular point, the tangent will look like this line, and the tangent will have an angle with the positive x-axis, tan inverse of this dy dx 1, that is 45 degree. Therefore, the normal at this particular point, its dy dx of that will be -1, which means that the normal over this will go 90 degree more. So it would be tan inverse -1, 135. So this is my normal. Now we take the gradient of this f, and gradient will be given by del f del x and del f del y, two elements. This is a vector quantity. If I calculate this del f del x and del f del y, then I see that this is 2x minus 2y minus 2, 4y minus 2 twice x. So you can see that negative of this 2x minus 2y minus 2 is here, and 4y minus twice x is here. So they are indeed related. And now we put this value -1, 1 in this gradient, and what we get is that at this point -1, 1, I have this 6, and -1, 1, I am putting a transpose because this is a column vector. So this will indicate the direction of the normal here. You can see that the normal is in 135 degree. So if I come here -1 and 1, I hit the normal. So this blue line is the normal, and I have to give a direction because I am talking about a vector here. So this is the vector direction. So in a sense that at a particular point, the gradient vector indicates the normal over the curve at that point, which is pointing outward. Now let us take up a family of curve. Here I have taken the same curve x square plus 2y square minus 2xy minus 2x equals 7, and that is our red line. And then I have taken the same equation, but I have changed the constants here, 27 and 63. So now you see that this del f gradient of f will be del f del x del f del y at t, and we know that if we take derivative here, that will give us 2x minus 2y minus 2, 4y minus 2x. Now if I take the gradient of g and p, that will give us also the same expression. So therefore, if I take the value of gradient of f at -1, 1, I get this 6, -1, 1, this vector. Now, because this expression is same for del f, del g or del p, at some other point, not necessarily at negative 1, 1, because other curves are not passing through this point, only red curves are passing. But this vector passing through this particular point, it will cut the other curves at some point, but we can clearly say that this vector will be normal to those curves as well. What I am trying to infer here, that this del g and del p will also be 6 minus 1 1 transpose. At some point it is not necessarily minus 1 1, and therefore this f, g and p, they must share the same normal, that is this vector minus 1 1. This vector should be normal to all three. So when I plot this vector, it will go through this origin. This is minus 1 1 point. It will cut this blue curve at some point. It will cut this green curve at some point. But this vector must be normal to all three of them. Now we want to move from, let us say, f to g or f to p, etc. Or we can move from p to g or g to f, etc. So we want to move from one curve to the other. And now we have, let us say, that we are walking from one curve to other and we have a constant speed. The question is that which path we can take to reach the other curve as quickly as possible. If we have constant speed, we have to take the shortest path. So which one is the shortest path? For example, if I take this minus 1 1 point as my center and I draw this circle which will just touch this blue curve, then I take this minus 1 1 point and I walk toward this blue curve in any direction. You can see that if I walk along this gradient line, I'll reach there faster, assuming that I am walking at same speed no matter where I go. This gradient path is the shortest path, because any other path you can see that they are crossing the circle. Any other path will cross the circle. Only the gradient path will simply touch the circle. Therefore, this gradient path is the shortest path. And similarly, if I go from this point to the outer curve, it is the same again. This is a long path. This is the short path here up to this, because this is the radius. Anything else is greater than radius. Anything else is greater than radius. So radius will be the shortest path. And radius path means we have to walk along the gradient. So the conclusion of this is that if I follow this gradient, what is happening here? I follow this gradient or any other path, the value of this is changing. On the red line, its value is 7. When I hit this blue line, its value is 27. When I hit this green line, the value is 63. So as I am going from this red line to outward direction, the value is actually increasing. And it will increase at fastest rate if we take this gradient direction. When we say fastest rate, we mean that we are walking along this path and we are walking at constant speed no matter what path we take. So if we take this gradient path, we'll reach the next curve faster than other because we have constant speed, and this gradient path is the shortest path. Now, a corollary of this is that because if we take the gradient path, the value of these functions increases at fastest rate. This value of this function will decrease at fastest rate if we go in the negative of gradient direction. And this is indeed the key in gradient descent based optimization. If we plot this f of xy as x square plus 2y square minus 2x minus 2xy, this is a 3D surface really. So I have this x and y here. For every x and y, I'll get a value of f, and I plot that f over this third axis, which is my f axis. What I'll get is that I'll get a surface like this. So this is a 3-dimensional surface. However, if I plot this x square plus 2y square minus 2x minus 2y equals constant, and I change this value of constant, then what I'll get is a lot of ellipses like this. So what is the connection between ellipse and this surface? Well, At this surface, if I cut this surface parallel to this xy plane, then at that particular parallel plane, f is a constant. And my cut, if I take a look from the top, it will look like an ellipse. And here we see that ellipse. So this ellipse, and in fact the family of these ellipses, something that we call is the contour plot of fxy. This contour plot is coming because I am cutting this three-dimensional surface at different values of f, and these are the different values of f. This 0 of f, I am cutting at 0 of f with my cutting plane is parallel to this xy plane. Then I'll get this particular line if I cut at f equals 0. Similarly, if I cut at f equals 5, I get this particular ellipse. If I cut at f equals 20, I get this particular ellipse, etc., etc. So this is our contour plot of this f is x square plus 2x square minus 2x minus 2xy, and this is the three-dimensional surface plot of the same. Now once we understand the relation, we have to see that to minimize this function fxy, we need not look at this surface plot. Rather, we can come in the contour plot and we can move opposite to this del f, del x, del f, del y, that direction means opposite to this gradient direction over this contour until we reach the minimum. This is indeed the idea which is extremely important in multidimensional optimization, and this is the key to gradient descent family of methods, which we will discuss in subsequent lectures. Now to summarize, we have identified that gradients play a major role in multidimensional unconstrained optimization, and in this lecture we have discussed the physical significance of gradient. For your exercise, you take a curve fxy is xy square, find the gradient at these points where this x vector is xy, two elements. Now directional derivative is something we call the inner product of a vector with the gradient. Therefore, we take the gradient at this particular point and then we take this as my direction. In this direction, find the directional derivative. So first you find the gradient and then you take the inner product with this direction. So that's all for this lecture. Thank you, and I'll see you in next class.